While molecules are not present in metals or ionic compounds, there are plenty of solids where distinct molecules can be identified. These are called molecular solids. Figure 8.30 from the textbook shows a diagram of diiodine, I2. The location of the nuclei can be found experimentally, and two different sets of distances appear in the structure. First, inside each molecule, note that the illustrator has drawn overlapping spheres. This represents a covalent bond between the atoms, as we would expect between two nonmetal atoms. There is a distance between the nuclei, which is labeled 2rCOV, or twice the covalent radius of the iodine atom. This is different than between nuclei in adjacent molecules. This distance is larger and is labeled 2rVDW, or 2 times the van der Waals radius. Note that the illustrator has not drawn overlapping atoms between one molecule and the next. This is because the only interaction here is the much weaker dispersion force, which is the only intermolecular force in a nonpolar molecule. There is again a relationship between strength of interaction and distance between nuclei. Looking again at our chart, we can now enter a third type of solid, the molecular solid. Some elements, like the diatomic halogens, and most covalent compounds crystallize as molecular solids. Here the unit is the molecule, as distinct molecules can be identified in the structure. One molecule is held to the next by weak intermolecular forces, dispersion, dipolar, and hydrogen bonding.